In the long history of computing, there are a few systems that get this legendary status, and VMS is right at the top of that list for being just unbelievably indestructible. We're talking about systems with uptimes measured in years. So what was the secret sauce? How on earth did its file system get to a level of reliability that, honestly, a lot of modern systems are still chasing? Well, let's dig in. And here's the cool part. The answers aren't some big mystery lost to time. They are all meticulously, beautifully documented in this book, Kirby McCoy's VMS File System Internals. And what it shows is that the stability of VMS wasn't magic. Nope. It was just brilliant, deliberate, and incredibly clever engineering. So that's really the big question we're tackling here. In our current world of super complex systems and, let's face it, pretty fragile data, what can we learn from the design that made VMS so rock solid? The answer, it turns out, is all about how it solved a massive performance problem without giving up even an ounce of safety. All right, so to really get how they pulled this off, we've got to go back and look at the problem they were facing. The early versions of VMS had a file system that, worked just fine on a single computer, but it was about to hit a wall, a very, very big wall. And that wall had a name, the Ancillary Control Process, or ACP. The best way to think about it is to imagine a gigantic highway, thousands of cars all trying to get through a single toll booth with one operator. That was the ACP. It was this one single central process that had to handle every single file request from every user on a disk. Yeah, not exactly a recipe for high performance, right? And then Digital goes and invents the VAX cluster. This was huge, a totally revolutionary idea that let a whole bunch of computers share the same disks. All of a sudden, the amount of traffic on that single-lane highway didn't just increase, it exploded. The ACP, which was already kind of creaking under the strain, just became a total system-wide traffic jam. It was completely overwhelmed. And this wasn't just, a minor slowdown. McCoy's text puts it bluntly. The ACP was a fundamental system-wide bottleneck. The very heart of the file system, the thing managing all the data, had become the single biggest thing holding the entire system back. Something had to give. And this is where the pure genius of the VMS engineers just blows you away. Instead of trying to make that one toll booth operator work faster, they did something way smarter. They decided to just blow up the toll booth completely and give every single car its own personal teleporter. And man, the shift was just night and day. On one side, you had the old ACP, centralized, single-threaded, a total bottleneck. And on the other, you have the new way, the XQP, a decentralized powerhouse. You go from one process for everybody to every single user getting their own file system process. It was a total flip from working in a line to everyone working in parallel. This solution was called the XQP, or Extended Queue I/O Processor. And here's the really clever bit. It wasn't some separate thing running in the background. It was a chunk of code that got merged directly into each user's own process. By doing that, VMS could suddenly handle thousands of file requests at the exact same time. Why? Because every user effectively had their own personal, dedicated file processor. Just like that, the bottleneck was gone. Okay, but wait. This brilliant solution creates a whole new and, honestly, a much scarier problem. If you've got hundreds, maybe thousands of processes all hitting the same disk at the same time, how do you stop them from just writing all over each other and turning your precious data into complete garbage? How do you prevent total and utter chaos? Well, the answer was another stroke of genius, the Distributed Lock Manager, or DLM. Just think of it as the ultimate all-powerful traffic cop for the entire cluster of computers. The DLM had one job and one job only: manage access. It made absolutely sure that even with thousands of things happening at once, only one process and one process only could get a right lock on any given chunk of data at any given moment. And that's the magic combo right there. The XQP gave it blinding speed by letting everyone go at once, in parallel. But the DLM provided absolute ironclad safety by making sure nobody ever collided. You got the best of both worlds, all the speed of a decentralized system with all the safety of a centralized one. But you see, all this clever architecture, it was all sitting on top of something even more important, a core philosophy. This wasn't just a random collection of cool features. The entire VMS file system was designed from the ground up with one guiding principle: data integrity comes first. Period. This quote from the book just says it all, doesn't it? It is imperative. That wasn't a goal or a nice to have. It was a command. The entire system was built on this non-negotiable idea that the user's data had to be correct and valid, all the time, no exceptions, no matter what. And they didn't just talk the talk. This philosophy was literally baked into the bits and bytes on the disk. VMS was, in the best possible way, completely paranoid about losing data. It kept multiple, redundant copies of its most critical files. It could automatically find bad spots on a physical disk and just work around them. It was constantly double and triple checking its own work to make sure what it wrote was actually what it was supposed to write. I mean, you can even see this obsession with order and safety in the simple way it finds a file. It's so clean and logical. It starts at a well-known front door on the disk, which points it to the master map of every file. That map points it to a specific blueprint for the file you want, which tells the system exactly where to find every last piece of data. It's predictable, it's hierarchical, and it's incredibly tough to break. So, what do we make of all this today? What's the legacy of a system that was designed over 4 decades ago? Well, it turns out the problems VMS was solving back then are the exact same problems we're still trying to solve today, just on a ridiculously bigger scale. Seriously, just think about it. The need for decentralized processing to handle huge workloads, that's the XQP. The need for a bulletproof, system-wide locking mechanism to keep data consistent across tons of different machines, that's the distributed lock manager. These ideas, which VMS pioneered for the VAX cluster, are literally the foundation that almost all of modern cloud computing and giant distributed databases are built on. And that really brings us to a final, pretty pointed question for today. In our mad dash for more speed, more features, and more complexity, have we managed to hang on to that simple, core VMS philosophy? Is data integrity still treated as the single most important feature, or has it become something of an afterthought? The legacy of the indestructible file system seems to shout that it should always be job number 1.